My name is Thomas Exner. I'm with the Applied Snow and Avalanche research crew at the University of Calgary. And I'd like to present a case study of an avalanche cycle from 2012 in early February, which was caused by daytime warming and in particular by strong solar radiation. First of all, I'd like to talk a little bit about the motivation behind this case study. A few years ago, the ASAR team developed a model to calculate the snowpack warming due to solar radiation. And basically, daytime warming is referred to the temperature difference in the snowpack at 10 centimeters snowpack depth between the coldest snow temperatures in the morning and the warmest temperatures in the afternoon. Swarm only calculates the temperature difference due to solar radiation, but does not incorporate effects on stability and avalanche activity, and that exactly was the motivation for this case study, basically to relate to an avalanche cycle where warming, in this particular case strong solar radiation, caused decreasing stability or heightened avalanche activity. So this slide shows a snapshot of the swarm model itself. It gives the daytime warming, again, due to solar radiation for different aspects, different slope angles, different time of year, depending on weather factors as cloudiness. Rapid daytime warming is one of the three major factors contributing to avalanching. According to a Swiss study which looked into a large data set of avalanches over 30 years, on days where more than 4 avalanches released, in about 20%, warming was a major contributing factor to avalanching. Canadian study, which was looking into avalanches over a time period of 10 years between 1997 and 2006, came up with similar numbers and concluded that in about 25% of fatal avalanche accidents, warming was a major contributing factor, not excluding loading due to new snow or redistribution due to winds. If those factors are excluded, there was still about 13% where warming had a major impact on those avalanche releases. So how does warming affect, for example, natural slab avalanche release? Let's say we have a slab sitting on a weak layer which is exposed to strong solar radiation. The surface or the near surface layers of the snowpack warm up and cause the snowpack to settle faster and creep faster in the downhill direction due to gravity. And that in turn causes higher deformation rates on a weak layer. And if those deformation rates are high enough, that might actually release a slab avalanche. The case study I will be presenting now covers the time period of February 1 to 5, 2012 in the Purcell Mountain range, one of the forecasting areas of the Canadian Avalanche Center. So first of all, we'll have a look at weather conditions for this time period. The weather forecast on February 1, the region may have seen the last drips and drabs of precipitation for a while, and a strong ridge building from the western part of the province will bring drier conditions for the forecast period. On this map, you can see a strong ridge feature building up on February 2, which intensifies over the following days over February 4 and 5 and develops into a stable high pressure area. This graph shows the average snowpack conditions within the Purcell mountain range. So about 40 to 80 centimeters of storm snow were sitting on the old snow surface from mid-January, which consisted of surface hoar, facets, crusts, and an old hard snow surface. The mid-pack was well settled and bridging over a layer from mid-December, which basically was a faceted old snow surface. And in some areas on the eastern side of the Purcell range in particular, a layer of basal facets was still causing some problems. So putting those two together, the weather forecast, they called for fairly warm conditions, and the snowpack structure, which consisted of a number of potential weak layers, resulted in an avalanche cycle as summarized by the Canadian Avalanche Center on February 4 as following. Since the recent warming, numerous large and destructive avalanches up to size 3.5 were reported in the region. Most of the avalanches were specific to south-facing alpine features. Some of these avalanches were initiated by cornice fall, others were loose, wet avalanches that in some cases stepped down to basal weaknesses. So in the following, we'll have a look in more detail what actually happened during the time period between February 1 to February 5. So first of all, we have a look at freezing levels or air temperature and cloudiness, which reflect the average weather conditions in the Purcell mountain range for this time period. On February 1, freezing levels were fairly low, still below 1,000 meters. On February 2, freezing levels rose up to approximately 1,000 meters to 1,300 meters. And on February 3, freezing levels rose way above 2,000 meters, which was basically not covered by the weather forecast. February 4, similar freezing levels, slightly lower, still in a range between 1,500 and 2,000 meters. And on February 5, freezing levels dropped down again to, in some areas, to valley bottom, but in most areas below 1,000 meters. February 1 was still overcast. In the following days, it started to clear, and it was fairly sunny until the end of this warming period. The daytime warming within the snowpack. So these two numbers here are the warming within the snowpack as calculated with the swarm warming model. The first number refers to a north-facing slope on 35 degrees, and the second number to a south-facing slope on 35 degrees. So we can see in February 1 there was a very insignificant warming of the snowpack north and south. On the following days, starting at February 2, on all the sunny aspects, there was significant daytime warming due to solar radiation within the snowpack. So now let's have a look at avalanche activity. On February 1, it was still fairly cold and overcast, and not much input due to solar radiation. There were no natural avalanches and no new skier-triggered avalanches observed. Only a couple explosive triggered avalanches indicated that the snowpack structure could potentially still be reactive. On February 2, with rising freezing levels and the first exposure of the snowpack to solar radiation, numerous natural avalanches up to size 3.5 released, which also affected deeper layers. Again, strong solar radiation and freezing levels rising above 2,000 meters caused the peak of the avalanche cycle with, again, numerous avalanches up to 3.5, which in some cases, some of these avalanches showed very wide propagation. Then surprisingly on February 4, with similar warming conditions as the day before, no new avalanches were observed. On February 5, with lowering freezing levels, but still a lot of strong solar radiation, again, no new avalanches were observed. So let's have a look again at February 2. With the onset of the warming and strong solar radiation, the avalanche cycle was initiated. And it seems like on the second day of the warming, where the avalanche cycle peaked, and most of the large avalanches were observed, the combination of very high freezing levels and strong solar radiation was the major driver for that. So again on February 4, even though warming conditions were similar to the day before, no new avalanches were observed. So it seems like that ongoing warming seems stabilizing for the snowpack. So what are the take-home points that we can learn from this case study? As long as there is a known instability within the snowpack, and you expose that the first time to strong solar radiation and combine that with rising freezing levels or rising air temperatures, then I would be extremely cautious to stay away from steeper open terrain. But to me, the big warning sign or the key factor is the onset of the warming or the first exposure to strong solar radiation, especially this time of year starting in February and later on. And as this case also has shown, to forecast this warming-induced avalanche cycle seemed to be very, very difficult. And here, last but not least, all the supporters and sponsors of the ASARC program.